ever actually stop to think about the space around you?
Like literally the space itself.
Right, exactly. I don't mean the things occupying the space. I'm not talking about the chair you're sitting in right now or the screen you're looking at. I mean the void, the actual physical space itself.
It's one of those things you just take for granted.
You completely take it for granted. But before a single particle can move from point A to point B, or before a magnetic field can ripple through the room, before any of the stuff of the universe can do its thing, what exactly is the stage where all of this reality is taking place?
And that question right there, it sounds almost too simple, like something you'd ponder as a kid looking up at the night sky. You know, before you learn to just accept the world as a given.
Yeah.
But that childlike curiosity actually hits on what is arguably the most profound, unresolved question in modern physics.
Because we're so incredibly accustomed to thinking of space as just an empty box.
Right, a passive container. We just dump matter and energy inside and sit back and watch them interact according to the laws of physics.
But the sources we are looking at today completely shatter that illusion. The space itself isn't a box. The space is the main character.
It really is.
So let's unpack this because that's the whole mind-bending premise of today's deep dive. We are shifting our perspective entirely to explore this paradigm in physics called geometry first.
Geometry first.
Yeah.
And the core idea here is that space, or more accurately, space-time, is not an empty stage at all.
It's an active participant.
Exactly. It's the ultimate rule book. It actively dictates what can exist and how it can exist, and honestly, what is fundamentally physically impossible.
And we're grounding this entire exploration in this really fascinating inquiry into physics. Specifically, we're going to look at something called the Bekenstein Bound.
Yeah, the Bekenstein Bound. And I should clarify, this isn't just about abstract mathematics living on a chalkboard somewhere.
Not at all.
It's about the literal physical limits of existence in our universe.
Yeah.
It dictates a maximum amount of reality you can literally cram into a given area.
Right. And I want to set the mission for today very clearly right up front. A major part of this deep dive is framed specifically as a note for researchers.
Yes, the six frontiers.
Exactly. The source material provides a brilliant roadmap outlining the 6 most critical open problems in fundamental physics today. So if you happen to be a physicist desperately searching for a groundbreaking thesis topic,
Consider this your masterclass.
yeah, consider this your masterclass. But honestly, even if you're just an insanely curious learner who wants to peer over the edge of human knowledge, this deep dive is your guide to the absolute bleeding edge.
And to anchor this whole journey, our source text uses a guiding philosophy from the legendary physicist Richard Feynman. He famously wrote a phrase on his blackboard right at the time of his death.
What I cannot create, I do not understand.
That's the one. And I think that's the perfect lens for us today. The goal isn't to get bogged down in impenetrable equations just to sound smart.
Right, we want to understand what nature actually does.
Following Feynman's spirit exactly. We want to look at the undeniable facts of reality and ask what they demand we believe about the architecture of the universe.
So let's start with this whole geometry first idea, because it really forces you to unlearn how physics is traditionally taught. I mean, in a standard high school physics class, space is just the vacuum.
It's just an X, Y, and Z axis.
Right. You put an electron in there, you apply a force, and you see how it moves. The space doesn't care.
It's just a background grid.
But geometry first argues that the shape of space-time is an active, demanding participant. It actually dictates how information is encoded in the universe.
If we trace the history of this twos, Albert Einstein really kicked off the revolution with general relativity in 1915. He was the first to realize that geometry is dynamic.
Mass tells space how to curve, and curved space tells mass how to move.
Exactly, the thing of the summation. But this geometry-first paradigm, especially in the decades following Einstein, takes that realization a massive step further. It suggests that geometry doesn't just push matter around. It literally constrains information.
And just to clarify for the listener, when we talk about information in physics,
Right.
we aren't talking about emails or Wikipedia articles.
No.
We're talking about the fundamental physical state of things, like the difference between an arrangement of carbon atoms that makes a lump of coal versus an arrangement that makes a diamond. That is purely a difference in physical information.
Precisely. Information is what distinguishes one physical microstate from another. So if geometry limits how much information can exist in a region, then geometry fundamentally limits reality itself.
It limits how complex an object can actually be.
Right.
To really get our heads around how this works, Our source breaks down the vocabulary of spacetime into 4 specific pillars. Let's walk through these because this is the language the rulebook is written in.
The foundational rules, yeah.
The first pillar is the metric tensor. Now that sounds like a piece of equipment from a sci-fi warp drive. What is a metric tensor in the real world?
So think of the metric tensor as the absolute baseline geometry of the universe. In mathematics, a tensor is just an array of numbers that describes how things relate to each other.
Okay.
The metric tensor is the specific mathematical object that defines distances and angles and volumes at every single infinitesimally small point in spacetime.
So if I imagine space as a giant 3D sheet of graph paper, the metric tensor is what actually defines the grid lines. It tells me what an inch or a meter actually is.
That's a really great way to visualize it, actually. It tells you exactly how far apart 2 points are taking into account time as well as space. It's essentially the Pythagorean theorem on cosmic steroids.
Wow.
Without the metric tensor, the concept of distance doesn't even exist. You can't say something is far away or close up. The metric tensor is the geometry.
Okay, that makes sense. The grid itself. The second pillar is curvature, and I assume this is how that cosmic graph paper deviates from being perfectly flat.
Yes. And curvature is where the phenomenon we experience as gravity enters the picture. In the Einsteinian view, gravity isn't an invisible magnetic-like tether pulling the Earth to the sun.
It's not a pulling force.
No, gravity is simply the curvature of that grid. A massive object like a star warps the metric tensor around it. The grid lines bunch up and stretch out.
So when the Earth orbits the sun, it isn't being pulled, it's just following the straightest possible line along a curved piece of graph paper.
Exactly. Curvature is just the physical manifestation of mass and energy interacting with the geometry.
Which brings us to the third pillar, which is causal structure. This feels like a big one. The source describes it as the network of what can influence what.
What's fascinating here is that causal structure is entirely downstream of the metric tensor. The geometry dictates the cosmic speed limit, the speed of light.
Right.
Light only travels along specific geometric paths called null geodesics. And because light is the fastest way information can travel, this creates what physicists call light cones.
Light cones. Okay, so if I clap my hands right now, that event sends a signal outward at the speed of light, creating an expanding sphere of influence.
Yes.
And if you map that expanding sphere over time, it looks like a cone.
And that cone represents the absolute boundary of your causal influence. If a star explodes in a distant galaxy today, but its light cone won't reach Earth for 1,000,000 years, then that explosion literally cannot affect us today.
Because the geometry doesn't connect the two events yet.
Exactly. So the rule is absolute. No geometry equals no causality. Things can only happen to other things if the geometric causal structure allows for the transfer of information.
That's a brilliant way to frame it. The universe isn't just a free-for-all. It's a strictly regulated network, which sets us up for the fourth pillar, and this is the one that really anchors the rest of our deep dive.
Holographic screens.
Right, holographic screens are boundaries.
This is where things start to feel very counterintuitive.
Yeah.
A holographic screen is the geometric skin of any region of space. Imagine drawing an invisible bubble around yourself right now. Just a mathematical sphere encompassing your body, the air immediately around you. That bubble is a bounding surface.
Okay, I have my invisible bubble.
In the geometry first view, these 2D surfaces, these screens, literally encode the absolute maximum amount of physical information that can possibly exist inside the 3D volume they enclose.
Wait, I want to pause here because that sounds completely backwards. You're saying the surface area of the bubble dictates what can happen inside the bubble.
That's exactly what I'm saying.
But we live in a 3D world. Surely the volume inside the bubble is what matters. If I have a bigger box, I can fit more stuff in it. This sounds like magic.
It does sound like magic, which is why it took physicists decades to accept it.
Hmm.
Let's apply your Feynman test. If we can't explain the physical mechanism, simply we don't understand it.
Right.
The core takeaway you need to hold on to before we look at the history is that geometry is not a passive stage. It is an active constraint. It forces reality to play by a specific set of rules, and those rules are written on the surfaces of things, not in their volumes.
Okay, to really understand why nature cares about surfaces and not volumes, we need to look at the sharpest, most unforgiving rule in that entire geometric rulebook, the Bekenstein Bound.
Yes.
To understand where this came from, we have to travel back to a very specific origin story.
The year is 1972. The setting is Princeton University. The landscape of theoretical physics at the time is deeply divided.
Because general relativity does a beautiful job explaining gravity and stars.
Right. And quantum mechanics does a beautiful job explaining atoms and particle physics.
But the two simply refuse to play nicely together.
Exactly. And in the middle of this tension is a brilliant graduate student named Jacob Bekenstein. He is working under the legendary physicist John Archibald Wheeler.
Wheeler was famous for his wild imagination, right? He actually coined the term black hole.
He did. And Bekenstein is obsessing over black holes, but he's looking at them through a very strange lens, classical thermodynamics.
Which at the time seemed completely absurd, right? Black holes were purely gravitational objects. Thermodynamics was the study of heat and steam engines and statistical mechanics.
Mixing the two was seen as a total category error.
But Bekenstein couldn't let go of a specific problem related to the second law of thermodynamics. And for the listener, the second law is arguably the most unbreakable rule in all of physics.
Absolutely.
It states that the total entropy of an isolated system can never decrease over time.
Entropy is often described as disorder, but a more accurate way to think about it in physics is as a measure of hidden information.
Okay.
Think of a pristine, perfectly stacked deck of cards. You know exactly where every card is, the entropy is very low. But if you shuffle that deck, you randomize it. The information about the original order is hidden. It's scrambled.
The entropy has increased.
Right. You can't naturally unscramble an egg.
Right.
A hot cup of coffee will always cool down and disperse its heat into the room, randomizing the air molecules. The universe constantly moves toward a state of higher entropy, higher hidden information.
So John Wheeler poses a thought experiment to his student Bekenstein. Our source calls it the coffee cup dilemma.
Yes. Wheeler essentially says, Jacob, suppose I have a hot cup of tea. It has a lot of entropy. The water molecules are jiggling chaotically. The steam is dispersing. Now suppose I take this hot cup of tea and I throw it directly into a black hole.
What happens to the entropy?
Exactly. According to the classical general relativity of 1972, a black hole is a completely smooth, featureless sphere of gravity. It has mass, it has spin, and it has an electric charge. That's it.
It has no internal structure that we can see from the outside.
It is the ultimate bald object.
Which means it has no hidden information, no disorder. According to classical physics, a black hole has zero entropy.
Do you see the crisis? If you throw a high-entropy cup of coffee into a zero-entropy black hole, the black hole swallows, it grows slightly larger in mass, but remains completely featureless.
The entropy of the coffee is gone, just vanished.
You just decreased the total entropy of the universe. You broke the second law of thermodynamics.
Which is a catastrophic problem for physics. Because if you can use black holes as cosmic trash cans to just delete entropy, then the foundational laws of thermodynamics are wrong and much of our understanding of the universe collapses.
So Bekenstein, this young grad student, realizes he has to save the laws of physics. He makes a profoundly radical proposal. He says, no, the information isn't deleted. Black holes must have entropy.
But if they have entropy, where is it stored? You can't look inside the black hole because nothing escapes the event horizon.
Bekenstein proposed that the entropy of a black hole, the hidden information of everything that ever fell into it, is encoded on its surface.
Wow.
He theorized that a black hole's entropy is directly proportional to the surface area of its event horizon. Not the volume of the abyss inside, but the 2D shell on the outside.
I can only imagine the pushback he got for that.
Oh, it was fierce. The most famous critic was Stephen Hawking. Hawking hated the idea. He pointed at a glaring flaw. If a black hole has entropy, the laws of thermodynamics dictate that it must also have a temperature.
Right.
And if it has a temperature above absolute zero, it must radiate heat. But the defining feature of a black hole is that nothing, not even light or heat, can escape it. So Bekenstein's idea seemed fundamentally contradictory.
But Hawking is a rigorous scientist. He didn't just dismiss it, he ran the math. He decided to apply quantum field theory to the curved spacetime around the event horizon to prove Bekenstein wrong.
And in doing so, Hawking proved Bekenstein spectacularly right. In 1974, Hawking discovered what we now call Hawking radiation.
Unbelievable.
He found that quantum fluctuations near the event horizon actually cause the black hole to emit a faint thermal glow. Black holes do have a temperature, they do radiate. And when Hawking finalized the mathematics, he found that the entropy of the black hole was perfectly precisely tied to its surface area.
It was a monumental triumph. It united thermodynamics, quantum mechanics, and gravity for the very first time. But Bekenstein didn't stop at black holes. He realized that if this logic applies to the most extreme objects in the universe, it must imply a universal rule for absolutely everything.
His reasoning was incredibly elegant. A black hole is the most dense possible concentration of matter and energy. Therefore, the mathematics that describe the entropy of a black hole must represent the absolute upper limit of entropy for any region of space.
Because you cannot have an object with more entropy than a black hole of the same size.
Right, because if you tried to pack that much information together, it would just collapse into a black hole anyway.
Which brings us to the actual formulas of the Bekenstein bound. We promised not to get lost in the weeds of the math, but we have to state the rules of the game to understand how reality is playing it.
Sure.
The classical version of the bound looks like this. The maximum entropy of a system is less than or equal to 2 pi times Boltzmann's constant times the radius of the system times its total energy, all divided by Planck's constant times the speed of light.
It's a beautiful equation because it takes fundamental constants from quantum mechanics, relativity, and thermodynamics and ties them together. But to really visualize what this means for the fabric of space, the source text introduces the holographic form of the formula. And this is the version that will fundamentally alter how you view the room you're sitting in.
Okay, wait at me.
The maximum information, the total number of bits that can exist in any region of space, is less than or equal to the boundary area divided by 4 times the Planck length squared.
Here's where it gets really interesting. We need to visualize the Planck length squared. The Planck area. What is that scale?
The Planck length is essentially the absolute smallest meaningful unit of distance in the universe. Below this scale, the concepts of space and distance break down completely. It is incredibly unfathomably small, roughly 1.6 times 10 to the power of negative 35 meters.
I always struggle with numbers that small. Let's visualize that 10 to the negative 35 scale. If a single atom were blown up to be the size of our entire visible universe, the Planck length will be roughly the size of a regular atom.
That is the perfect analogy. So take that unimaginably tiny length and draw a square. 1 Planck length by 1 Planck length. That is a Planck area.
And the holographic formula says that if you draw an invisible boundary around any physical object, a coffee cup, a planet, or your own body, you can divide that surface area into a grid of these tiny Planck squares.
And here is the profound, inescapable conclusion. Each one of those infinitely tiny geometric squares can hold exactly 1 bit of physical information. A 1 or a 0, on or off. The surface of space itself is pixelated.
The pixelation of space. It's like walking up to a pristine 8K television screen, getting so close that your nose touches the glass, and realizing that the smooth, continuous picture of reality is actually made of distinct individual tiny dots.
Exactly.
But we aren't talking about a TV screen. We are talking about the fundamental fabric of the cosmos. The maximum amount of information you can possibly fit inside any 3D volume is strictly mathematically limited by the number of 2D pixels on its outer surface.
This raises an incredibly important question. One that our source explicitly says should keep theoretical physicists up at night. Why area and not volume? We live in a 3-dimensional world. We move in 3 dimensions. Why does the universe care about the 2D surface area of a region rather than the 3D volume inside it?
If information is just stuff inside a container like packing clothes into a suitcase, you would naturally assume you could keep packing more stuff into the volume. If I buy a bigger suitcase, I expect the capacity to scale with the volume.
Volume grows as a cube.
Yeah, if you double the dimensions of a box, the volume increases by a factor of 8. But the surface area only increases by a factor of 4. Why is nature shortchanging us on storage space?
To understand why, we have to look at what physically happens when you try to fight the Bekenstein Bound. Let's do a thought experiment. Imagine you are an advanced godlike engineer. You decide you don't care about the holographic limit.
Okay.
You build an incredibly advanced data compression machine, and you try to pack more physical bits of information into a spherical volume than the pixelated boundary area allows.
So to pack more bits of physical information into a space, I have to add more distinct physical states. I have to pump more matter or more energy into that space. I'm taking massive amounts of particles, laser beams, hard drives, and compressing them down into this sphere.
Exactly. And as you keep packing matter and energy into that tightly confined volume, what happens to the density of that region?
The density skyrockets. It becomes incredibly massive.
And as the mass density skyrockets the curvature of space-time, the metric tensor we talked about earlier begins to warp violently. General relativity takes over.
Oh, I see where this is going.
Eventually, long before your data compression machine can ever exceed the Bekenstein limit of that volume, the mass energy within that region becomes so unbelievably dense that the geometry of space-time collapses in on itself.
It forms a black hole.
It forms a black hole.
Right.
And the precise moment it collapses, a brand new event horizon is created, a new geometric bounding surface. And if you calculate the area of that newly formed black hole horizon, it perfectly precisely caps the entropy at the exact limit of the holographic formula.
Nature steps in. Gravity is the enforcer. That gives me absolute chills. Geometry isn't just a stage, it's the cosmic police force.
Yes.
When you try to break the information limit, space-time literally restructures itself, tears a hole in reality, and quarantines your experiment behind an event horizon to prevent you from violating the limit.
It's a brilliant self-defense mechanism of the universe.
Yeah.
And it reveals something incredibly deep. It shows us that gravity, space-time geometry, and quantum information are not three different phenomena that just happen to interact with each other.
They are three facets of the exact same underlying architecture. Gravity is the limit of information density.
Exactly.
Okay, I think we have the theoretical foundation locked in. Space's pixelated area dictates capacity, and gravity enforces the rules. Let's bring this down from the realm of abstract thought experiments to a scale we can actually visualize.
Yeah, let's look at some numbers.
Our source text provides this amazing section called Universal Accounting. We're going to look at concrete examples of physical objects in our universe and compare their actual physical complexity to their maximum geometric information capacity based on the Bekenstein bound.
We are asking the fundamental question: how much reality can literally exist in these spaces?
Exactly. Let's start incredibly small. The proton. It's the building block of atoms.
A proton has a radius of roughly 10 to the negative 15 meters. It is infinitesimally small. But if we calculate the 2D surface area of a proton and apply the Bekenstein holographic bound, dividing that area by the Planck area, it turns out the geometry of a proton could theoretically hold roughly 1 million bits of information.
Yeah.
10 to the 6th power bits.
1 million bits. But wait, I'm struggling with that. In standard particle physics, a proton isn't that complex. It has a handful of known quantum numbers. It has a positive charge. It has a specific mass. It has a spin of 1/2. Even if we look inside it at the quarks and gluons, the fundamental particles that make up the proton, we're only talking about a few dozen bits of information needed to perfectly describe a proton's state.
You've hit on exactly why this accounting is so fascinating for researchers. The proton has a massive informational budget of 1 million bits, but it appears to be using almost none of it. It is incredibly sparse.
So it's basically an empty hard drive.
Yes. From a research perspective, this huge geometric headroom strongly suggests two possibilities. Either the fundamental particles of our universe are just incredibly simple and inefficiently packed, or there is deep, complex substructure inside the proton physics far beyond quarks and gluons that we simply haven't built colliders powerful enough to access yet. The space is there waiting to be used.
That's a tantalizing thought for particle physicists.
Yeah.
Okay, let's scale up from the quantum realm to something very relevant to the listener. Let's calculate the information capacity of the human brain. An average adult brain has a radius of roughly 0.1 meters. If we draw our invisible holographic boundary purely around the geometric space your brain occupies, how many bits of information could it fundamentally hold?
According to the Bekenstein Bound, a spherical region the size of a human brain has a surface area capable of holding 10 to the 68th power bits of information. That is a 1 followed by 68 zeros.
10 to the 68th bits. Let's put that in context. Neuroscientists estimate that the human brain has roughly 86 billion neurons connected by maybe 10 to the 15th power synaptic connections. Even if we account for the quantum states of every single molecule in the brain, the actual biological complexity is a tiny microscopic fraction of 10 to the 68.
It is unfathomably larger.
Honestly, on a Monday morning before coffee, my brain feels like it's operating on about 4 bits of information: hot, cold, tired, and hungry.
Right.
But the geometric capacity is 10 to the 68th. It really highlights how biology, despite feeling so complex to us, is actually an incredibly sparse macroscopic phenomenon compared to the raw informational capacity of spacetime.
Very true.
You, the listener, are mostly empty space. And I don't just mean the physical distance between the nucleus of your atoms and your electrons. I mean in terms of the pure computational reality your geometric footprint could theoretically hold, you are almost entirely an empty hard drive.
Moving up the scale, let's look at the Earth. The entire planet has an informational capacity of 10 to the 74th bits. What's fascinating here is that this number vastly exceeds the total number of physical atoms in the Earth, which is roughly 10 to the 50th. Even if every atom held millions of bits of data, It wouldn't scratch the surface of the geometric limit.
In the solar system, if we draw a bubble around the orbit of Neptune,
The geometric capacity of the solar system is 10 to the 87th bits.
and what if we take it to the absolute limit, the entire observable universe, everything we can see? We have a cosmic horizon with a radius of roughly 4 times 10 to the 26 meters. If we draw a massive holographic screen around the entire edge of our vision into the cosmos, what is the Bekenstein bound of reality itself?
The maximum information capacity of the observable universe is exactly 10 to the 123rd bits.
10 to the 123rd bits. I want everyone listening to just pause and let that number sink in. It's a massive number, sure, but the most important thing about it is that it is finite.
It is not infinity.
Every star that has ever burned, every galaxy swirling in the dark, every thought you've ever had, every tragic historical event, every microscopic interaction of every particle since the Big Bang, all the physics, all the history, all the structure of our entire reality fits within that hard upper limit.
It is the ultimate storage capacity of our specific universe.
So we've looked at all these objects, protons, brains, planets, the universe, and they all have massive amounts of unused space. Is there anything in the universe that actually uses its full budget? Is there any object where the physical complexity equals the geometric limit?
Yes, there is exactly one class of objects in the entire universe that utilizes its full budget. We've already talked about them. Black holes.
Of course.
A black hole's entropy is exactly equal to its surface area divided by 4 Planck lengths squared. They perfectly saturate the bound.
They are completely physically full.
Precisely. You cannot fit a single extra bit of information, not even a single electron's worth of data, into a black hole without expanding its surface area by exactly 1 Planck pixel to accommodate it. They are the densest objects the universe permits.
So what does this universal accounting mean for the nature of reality? If we know the absolute limits, what do we do with that knowledge? This brings us to a concept the source calls the ontological force and negative accounting.
To understand the power of this, we need to make a strict philosophical distinction between an engineering limit and an ontological fundamental limit.
Okay.
An engineering limit is like the storage on your laptop. You buy a computer with a 1 terabyte solid-state drive. You can't put 2 terabytes of photos on it. Why? Because of how the silicon wafers are manufactured by human engineers.
Right. It's the limit of our current technology or our budget. But there's no law of physics preventing me from buying a bigger hard drive or plugging in an external drive. It's just a practical hurdle.
Exactly. But the Bekenstein bound is an ontological limit. Ontology is the branch of philosophy that deals with the nature of being of what actually exists. The bound dictates what configurations of matter, energy, and information are physically possible to exist at all in principle, regardless of technology.
Nature doesn't care about your engineering goals. She has rules, and they are mathematically written into the metric tensor.
So if you are a theoretical physicist or an artificial intelligence researcher or a cosmologist, and you propose a mathematical model of a system, say a hyper-advanced quantum computer or a theoretical model of an alternate universe, and your math requires more physical bits of information than the bounding surface of that system allows, your model is wrong.
It's not just hard to engineer.
No, it is a fantasy. It's fundamentally forbidden by the geometry of space itself.
This realization leads us to the holy trinity of this entire theory. The source text calls it the deep equivalence.
This is the realization that geometry, information, and physics are not 3 distinct disciplines that merely overlap. At the deepest level, they are the exact same thing, just viewed from different mathematical angles.
Let's break that down because it's a massive claim. First, geometry equals information.
Yes. Based on the holographic principle, the physical area of a bounding surface is the information capacity of the enclosed region. Area and information are completely synonymous. You can measure a black hole's surface in square meters, or you can measure it in terabytes.
That's wild.
Furthermore, the curvature of spacetime, which we experience daily as the force of gravity holding us to the Earth, is literally the geometric gradient, the slope of how information flows through the universe.
Okay, second part of the trinity, information equals physics.
Because what is physics fundamentally? Physics is simply the set of rules governing how physical information changes from one state to another over time. The laws of thermodynamics, like the second law we discussed with the cooling coffee cup, don't need to be assumed as fundamental laws anymore.
Oh, I see.
They can actually be mathematically derived purely from the geometry of these holographic horizons. Thermodynamics emerges from geometry.
So if we accept this deep equivalence, it allows us to perform what the source calls negative accounting. We can look at theoretical ideas and conclusively rule them out. We can say what is physically impossible.
Right, what's forbidden?
I'm going to list these out for you, the listener, because understanding what cannot exist is often the key to understanding what does. Number one, no physical system can exceed its bounding surface information, period. If it tries, it becomes a black hole.
Yep, we covered that.
Number two, no continuous reality exists below the Planck scale. Because space is pixelated, physics is fundamentally granular.
Think about what that implies. We are used to thinking we can always zoom in closer. But if you try to zoom in past a single Planck length, there is nothing there. There is no smooth, continuous reality underneath. It's just discrete, indivisible bits.
Number three, information cannot move faster than causal structure allows. We often casually think of the speed of light as just a speed limit for fast objects like photons or rockets. But truly, it is a geometric limit on the transfer of information. Causality is purely geometric.
Number four, any true theory of common erasure. Any theory of quantum gravity cannot be volumetric. This is a huge blow to a lot of older theoretical physics models from the 20th century. Since we know information scales with area, not volume, the ultimate theory of reality must be holographic in nature.
And number five, which is honestly my favorite philosophical takeaway, infinite complexity is a physical impossibility.
Right.
Nothing in our physical universe can be infinitely complex. Not a fractal, not a brane, not a chaotic weather system, because absolutely everything is bounded by a finite surface area containing a finite number of bits. Infinity might exist as a mathematical concept on a chalkboard, but it does not exist in the physical geometry of our universe.
Which brings us to a major critical pivot in our deep dive. We have established the foundation. We understand what geometry first means. We understand the Bekenstein Bound. We understand the pixels of space, and we understand the limits of what can exist. Now we are shifting to the core focus of this entire discussion, the reason this source material was compiled.
Yes. The note for researchers. For you listening, whether you are a PhD student looking for a dissertation or just someone who wants a front row seat to the future of science, this is it. The foundational knowledge is set. Now we are going to lay out the actual landscape of open problems in physics.
The 6 specific frontiers from our source text.
Exactly. These are the active battlegrounds and the intellectual war zones where the brightest minds on Earth are trying to finish writing the ultimate rulebook.
We need to spend real time on each of these because they represent the bleeding edge of human thought. Let's start with direction 1. Holographic quantum gravity, specifically looking at a mathematical framework called AD-SCFT.
Okay, AD-SCFT. That is an intimidating acronym. Let's unpack the history first. This was a massive earthquake-level breakthrough in physics in 1997, published by an Argentine physicist named Juan Maldacena. What exactly did he do?
Maldacena provided the most rigorous, mathematically precise realization of the holographic principle we have ever seen. We've been talking about the idea that a 2D surface encodes a 3D volume. Maldacena proved it mathematically.
He actually proved it.
Yes. He showed that a specific theory of gravity operating in a volume of space is exactly 100% mathematically identical to a quantum field theory operating solely on the boundary of that space.
Let's define these terms so we don't lose anyone. What is the AD-DS part?
AD-S stands for anti-de Sitter space. It's a specific type of geometric space that has a negative curvature.
Negative curvature, like the shape of a saddle.
Exactly. Or if you've ever seen those famous M.C. Escher drawings of bats and angels arranged in a circle where they get infinitely smaller as they reach the edge of the circle, that is a 2D representation of anti-de Sitter space. It's a beautifully symmetric mathematical playground, but it has a very distinct boundary.
And what is the CFT part?
CFT stands for conformal field theory. This is a type of quantum mechanics theory that has no gravity in it whatsoever. It operates perfectly flatly, and it is conformal, meaning it looks the same, no matter how much you zoom in or zoom out. It is scale invariant.
Okay, so I want to try an analogy here to see if I have this right. The classic analogy is a can of soup. The soup inside the can is the 3D volume. That's the anti-de Sitter space. It has chunks of vegetables moving around. Gravity is acting on them. Things are bumping into each other. That's the ADS bowl.
Yes, perfectly stated.
And the label wrapped around the outside of the can is the 2D boundary. That's the conformal field theory. It's flat. There is no gravity on the label.
That is a perfect visualization.
Yeah.
And what Maldacena proved, and this is why he is a legend, is that if you write out the incredibly complex mathematical equations for the chunks of soup interacting with gravity inside the can, and then you write out the completely different equations for the flat, gravity-free quantum interactions happening on the label, They are the exact same equations in disguise. You can translate perfectly between them.
So a 3D universe with gravity is mathematically identical to a 2D surface without gravity. He literally proved that holography works.
He built a perfect mathematical dictionary between geometry and quantum mechanics. But here is the research note, the massive unsolved problem that needs a brilliant mind to tackle it. Anti-de Sitter space, that negatively curved Escher painting, is an incredibly useful toy model for physicists. But it is absolutely not the universe we live in.
Right. We know from astronomical observations that our universe is expanding and the expansion is accelerating.
Exactly. Our universe has a slight positive curvature, which is called de Sitter space, and on very local scales, it looks almost perfectly flat.
So neat to researchers. We know the holographic dictionary works beautifully in the negatively curved toy model of anti-de Sitter space. Your mission, should you choose to accept it, is to prove it works for flat space, or for our actual expanding de Sitter universe. We need a dictionary that translates the 3D physics we experience locally from the boundary data of our real cosmic horizon. We need the real soup can.
Moving to direction 2, and honestly, this one might be the most mind-bending concept in modern physics. The frontier is entanglement and spacetime geometry. The shorthand equation for this research direction is ER equals EPR.
ER equals EPR. That sounds like an equation from a parallel universe where Einstein just combined all his acronyms. Let's break this down. In 2013, Juan Maldacena teamed up with Leonard Susskind, another titan of physics. They looked at two incredibly weird, seemingly unrelated phenomena that Einstein himself wrote papers about in 1935. Let's start with the EPR side.
EPR stands for Einstein-Podolsky-Rosen. It was a paper they wrote to point out what they thought was a fatal flaw in quantum mechanics: quantum entanglement. Entanglement is the phenomenon where two quantum particles, say two electrons, become intimately connected in such a way that measuring the spin of one instantly determines the spin of the other, even if they're separated by billions of light years.
Einstein hated this. He famously called it spooky action at a distance because it seemed to imply that information was traveling faster than light, violating causality. He thought it meant quantum mechanics was incomplete.
Exactly. That's the EPR side. Entanglement. Now the ER side. In that exact same year, 1935, Einstein and Nathan Rosen wrote another paper completely unrelated, exploring the math of general relativity. They realized that the equations allowed for tunnels connecting two distant points in spacetime.
Einstein-Rosen bridges. Wormholes. The staple of every sci-fi show ever made.
Yes, so you have EPR, which is quantum entanglement, a spooky connection, and ER, which are wormholes, a geometric tunnel. For 78 years, these were considered two entirely separate fields of study. One is quantum mechanics, the other is gravity.
And what did Maldacena and Susskind propose in 2013?
They proposed the simplest, most audacious equation. ER equals EPR. They are the exact same thing.
Wait, are you saying that quantum entanglement is a wormhole?
Yes. They proposed that when two particles are entangled in a lab, they are literally physically connected by a microscopic geometric wormhole in the fabric of spacetime. The spooky connection isn't magic, it's a hidden geometric tunnel.
That is staggering. It means that space-time geometry isn't just a container that quantum mechanics happens inside of. Geometry is literally woven out of quantum entanglement. The more entanglement you have, the closer things are together. Space is built from entangled threads.
There's beautiful mathematical evidence for this, specifically something called Ryu-Takanagi minimal surfaces.
Okay, what is a Ryu-Takanagi minimal surface?
It's named after the two physicists who discovered it. Think about blowing a soap bubble. The soap film naturally finds the shape with the absolute minimum surface area to connect the plastic wand, a minimal surface.
Right.
Ryu and Takanagi proved mathematically that if you draw one of these minimal surfaces through the bulk geometry of a space, the area of that geometric surface perfectly computes the exact amount of quantum entanglement happening on the boundary.
Area computes entanglement. It ties right back to Bekenstein's area formula, geometry equals information.
So here is the research note for direction 2.
Yeah.
We have the ER equals EPR hypothesis. We have Ryu-Takanagi. But we need to map the specifics. We need researchers to figure out exactly how the individual Planck scale pixels of the Bekenstein Bound act as the fundamental degrees of freedom for entanglement.
How it all pieces together.
Right. If geometry is built out of entanglement, how exactly do those 10 to the 123rd discrete bits on our cosmic horizon weave themselves together to create our macroscopic experience of distance, time, and gravity? Solving the exact mechanics of that weaving process is the key to unifying quantum mechanics and gravity.
Whoever solves that gets a Nobel Prize guaranteed. All right, let's look at direction 3, entropic gravity and emergence.
This frontier takes us to a highly controversial proposal put forward by theoretical physicist Eric Ferland in 2010. Berlin looked at all the holographic math we've discussed, area, entropy information, and he asked a truly radical question. What if gravity isn't a fundamental force of nature at all?
Hold on. Gravity isn't a fundamental force. It's the force that holds my feet to the ground. It holds the moon in orbit around the Earth. If it's not a fundamental force pulling things together, what else could it possibly be?
Berlin argues that gravity is an emergent thermodynamic effect. To understand emergence, think about temperature. If you look at a single isolated helium atom floating in a void, it does not have a temperature. The concept of temperature doesn't exist at the fundamental particle level.
Because temperature is about movement.
Yeah, exactly. Temperature only emerges as a macroscopic property when you have billions of atoms bouncing around and colliding with each other. It's a statistical illusion of microscopic movement.
Okay, so a single atom doesn't have a temperature, but a cup of coffee does.
Exactly. Or think of a rubber band. Why does a stretched rubber band pull back when you let it go? It isn't because there's a fundamental rubber force pulling the molecules together. It's because the long polymer chains in the rubber naturally want to return to a curled up, highly entangled, high entropy state. The pulling force you feel is just the thermodynamic statistical push toward higher entropy.
And Verlin says gravity is doing the exact same thing.
Yes. He proposes that when an apple falls from a tree to the Earth isn't exerting a fundamental gravitational pull on the apple. Instead, as the apple moves closer to the massive Earth, the total entropy of the holographic screen surrounding the apple and the Earth increases. The universe naturally seeks the state of highest entropy.
So the apple falling is just the universe naturally sliding down a thermodynamic hill to maximize hidden information. Gravity is just an entropic force.
That's the theory.
Things falling is just the universe naturally seeking higher entropy on its geometric boundaries. That is unbelievably elegant. It completely removes the need for hypothetical particles like gravitons. It turns gravity into a pure thermodynamic consequence of information geometry.
It is breathtakingly elegant. But here is the research note, and it's a big one. This theory is a fierce active battleground. While entropic gravity beautifully derives Isaac Newton's laws of gravity and Einstein's equations from pure thermodynamics, it severely struggles when we point our telescopes at the sky.
What's the problem?
Dark matter. When we observe how galaxies rotate, there appears to be a massive amount of invisible mass holding them together. Standard gravity requires the invention of dark matter particles to explain it. Verlin hoped his entropic theory would explain the extra gravity without needing dark matter.
Did it work?
So far, the entropic models struggle to precisely match the highly detailed astronomical observations of dark matter distributions, like the cosmic microwave background or gravitational lensing.
So the challenge for researchers in Direction 3 is this. Can entropic gravity be refined and expanded to perfectly explain the massive cosmic scales of galaxy clusters? Or is its derivation of Newton's laws just a tantalizing, coincidental mathematical mirage?
Exactly. It needs to be tested to the breaking point, which
Where?
flows nicely into Direction 4, the firewall paradox and information preservation. This is perhaps the most dramatic, high-stakes intellectual conflict in physics today.
To understand the firewall paradox, we have to go back to Stephen Hawking and black holes. In 1974, Hawking proved that black holes evaporate. They leak Hawking radiation. Slowly at first, but over trillions of years, a black hole will radiate away all of its mass and completely vanish into nothingness.
But this evaporation creates a massive catastrophic contradiction between the two great pillars of physics, quantum mechanics and general relativity. It revolves around the fate of information.
Right. Let's do another thought experiment. Suppose I have a highly classified diary full of complex information. I throw my diary into a black hole. According to general relativity, the diary passes the event horizon and falls toward the center. Then, over trillions of years, the black hole evaporates by emitting Hawking radiation.
But Hawking's original calculations show that this radiation is perfectly thermal. It is completely random heat. It contains no structured information whatsoever.
So the black hole swallows my complex diary and eventually turns entirely into random heat. The black hole is gone, the diary is gone, and the radiation is gibberish. The information in my diary is permanently erased from the universe.
And this is where quantum mechanics violently objects. Quantum mechanics is built on a foundational principle called unitarity. Unitarity strictly demands that physical information must always be preserved in the universe. You can burn a diary, you can scramble it, you can turn it to ash, but in principle, if you tracked every photon and every carbon atom, you could reconstruct the text. Information cannot be deleted.
So we have a war. Relativity says the black hole destroys the information. Quantum mechanics says it must be preserved in the outgoing radiation. Most physicists today side with quantum mechanics. They believe the information must somehow be encoded in the Hawking radiation.
But in 2012, a group of 4 theoretical physicists, Almhiri, Marov, Polchinski, and Sully, known collectively by their initials as the AMPS group, dropped a bomb on the physics community. They published a paper pointing out a fatal flaw in the idea that information escapes.
What was the flaw?
It relies on something called the monogamy of entanglement. For the information to escape the black hole, the outgoing particles of radiation must be highly entangled with each other. But for the event horizon to be a smooth, normal region of space as general relativity demands, the outgoing particles must also be highly entangled with particles falling into the black hole.
Let me guess. A particle can't be fully entangled with 2 different things at the same time.
Exactly. Quantum monogamy. AMPS proved that you cannot satisfy both conditions. If you insist that the information escapes, you have to break the entanglement across the event horizon. And breaking that entanglement releases an unbelievable infinite amount of energy.
A firewall.
Yes. The AMPS paper showed that to preserve information, a literal wall of infinitely high-energy plasma, a firewall, must exist exactly at the event horizon of every black hole.
But wait, that violently breaks Einstein's equivalence principle. Einstein said that free falling is indistinguishable from zero gravity. If I fall past the event horizon of a supermassive black hole, I shouldn't even notice. It should be a smooth transition. But AMPS says I would hit an infinite wall of fire and be instantly incinerated into ash.
This is the paradox. You are forced to choose your poison. Do you throw away quantum mechanics and allow information to be destroyed? Or do you throw away general relativity, create a firewall, and destroy the equivalence principle? You cannot have both.
So what is the research note for direction 4?
The note for researchers is to resolve the paradox. Save physics. Researchers must figure out exactly how information is dynamically encoded at the event horizon, strictly abiding by the Bekenstein Bound's pixel limit in a way that allows it to escape without violating quantum unitarity and without creating a relativistic firewall that incinerates astronauts.
Sounds easy enough.
Right. The source text suggests the answer almost certainly lies in fully embracing the geometry-first framework, perhaps involving the ER equals EPR wormholes we discussed earlier. But the exact mathematical mechanism is entirely unknown. It is the greatest puzzle in theoretical physics.
Which flows perfectly into direction 5, which might offer the tools to solve it. Quantum error correction and spacetime.
When I first read about this, I thought I was reading a computer science textbook, not a physics paper.
It essentially is computer science.
Yeah.
Let's explain error correction for the listener. If you send a text message or save a file to a hard drive, you are relying on classical error correction. The real world is messy. There's thermal noise, cosmic rays, magnetic interference. These things can occasionally cause a bit in a computer to flip from a 1 to a 0 by accident. That's data corruption.
To prevent your photos from being corrupted by random noise, computer engineers use error-correcting codes. The simplest version is a repetition code. Instead of storing a 1, the computer stores a 111. If a cosmic ray hits and flips 1 bit so it reads 101, the computer's algorithm looks at it, sees 2 1s, and 10 takes a majority vote and automatically corrects the error back to 111.
The information is stored redundantly smeared out across multiple physical locations, so local damage doesn't destroy the global message.
In quantum computing, doing this is vastly more complicated because you can't just copy quantum states. There's a rule against it called the no-cloning theorem. But brilliant physicists developed quantum error-correcting codes to protect fragile quantum computations.
And this is where the mind-blowing discovery happened. In 2015, 3 physicists, Almhiri, Dong, and Harlow, were studying the holographic ADIA CFT correspondence we talked about earlier. They were looking at how the physics in the 3D bulk volume is mathematically generated by the information on the 2D boundary label.
And what they found is stunning. They realized that the complex mathematics translating the boundary into the bulk matched something they had seen before. The equations were perfectly fundamentally identical to the mathematical architecture of a quantum error-correcting code.
Space-time geometry is literally a quantum error-correcting code. I mean, that absolutely blows my mind.
It means that the existence of a particle deep inside the 3D volume of our universe isn't stored in just one local spot on the 2D cosmic boundary. The data of that particle is smeared out and redundantly encoded across vast regions of the holographic screen. If you somehow deleted or damaged a portion of the boundary information, the universe could perfectly reconstruct the 3D physics using the redundant data from the rest of the boundary.
The universe is actively running a computational error correction algorithm to maintain the stable illusion of 3D reality. It's like the universe is constantly rendering the graphics of space-time and double-checking its math so the simulation doesn't crash.
So the research note for Direction 5 is clear. Fully map this architecture. If space-time is an error-correcting tensor network, we need researchers to reverse engineer the code. What specific class of quantum codes is the universe running? If we can translate general relativity entirely into the language of quantum information theory, we will finally reveal quantum gravity not as a fundamental force of particles bumping into each other, but as a pure information theoretic construction.
And that brings us to our final frontier, Direction 6. Complexity equals volume and action.
We owe this final profound proposal to Leonard Susskind as well. We have spent this entire deep dive talking about area. We established that the surface area bounds the entropy, the hidden information. But there's a temporal problem with entropy in black holes.
What's the problem?
When a black hole forms, it reaches its maximum entropy state incredibly fast. Basically, a fraction of a second after the star collapses, the surface area stabilizes, and the entropy is maxed out. From the outside, the black hole looks like it has reached thermal equilibrium. It's done changing.
But inside.
But inside the quantum state of the particles that fell in continues to evolve. The microscopic states become increasingly scrambled, increasingly entangled, and computationally vastly more complex. And this computational complexity continues to grow for an unimaginably long time, exponentially longer than the current age of the universe.
So Susskind realized there was a mismatch. If the surface area represents the entropy and the entropy stops growing, what geometric feature represents this continuously growing computational complexity? If geometry equals information, some piece of the geometry must be growing.
Exactly. And he proposed that complexity equals volume conjecture. He theorized that the computational complexity of the quantum state is directly proportional to the physical volume of the Einstein-Rosen bridge, the wormhole interior of the black hole.
Wait, the inside of a black hole grows?
According to general relativity, yes. While the outer surface area of the event horizon stays completely fixed, the internal geometry of the space inside the black hole continues to stretch and expand over time like cosmic taffy.
So the surface area is the storage capacity, like the entropy, but the expanding internal volume is the processing depth, the complexity.
He later refined it to a related physical property called action, but the core idea remains. The stretching of interior spacetime is the physical manifestation of quantum circuits executing operations.
So the research note for Direction 6. We have established that the holographic boundary tells us everything about the capacity of the system. But researchers need to use this complexity equals volume conjecture to actually peer inside the event horizon. If area gives us the boundary limit, understanding the evolution of geometric volume might be the key to understanding the deep interior physics of incredibly old black holes.
If we take a step back and connect all 6 of these frontiers, ADS-CFT, holography ER equals EPR wormhole entanglement, entropic gravity, the AMPS firewall spacetime, as error correction and complexity equaling volume, you don't just see a random list of problems. You see a highly cohesive, unified research program. The tools of quantum computing and information theory are literally becoming the tools of fundamental geometry.
Okay, we've been incredibly deep in the theoretical weeds. This has been a masterclass in high-level physics. But let's bring this back down to earth for a moment. Sectioning off the theory, let's look at the practical stakes. Why should you, the listener, sitting in your car or walking your dog, care about the holographic principle and Planck scale pixels? Does any of this matter outside of a theoretical physics department?
It absolutely matters because these theories dictate the absolute uncompromising limits of all future human technology and our ultimate understanding of our place in the cosmos. Let's look at the real-world implications, starting with computation. We are currently pouring billions of dollars globally into building quantum computers, striving for exponential leaps in processing power.
Right, the tech industry assumes Moore's law or some quantum version of it will just continue forever.
But the Bekenstein Bound operating alongside another physical limit called a Bremerman limit violently disagrees.
What is the Bremerman limit?
Hans Bremerman was a mathematician who applied quantum mechanics and relativity to computation. He calculated the absolute maximum computational speed of a self-contained system in the physical universe based on its mass and energy. He found it is roughly 1.36 times 10 to the 50th power bits per second per kilogram.
Okay, so the Bremerman limit dictates the absolute maximum processing speed based on mass, and the Bekenstein bound dictates the absolute maximum storage capacity based on surface area.
Exactly. Together, they define the absolute unbreakable geometric ceiling for computation. It doesn't matter if we invent miraculous new quantum metamaterials or if we discover an alien civilization a million years older than us. Every microchip, every quantum processor, every artificial intelligence server farm ever built by anyone in this universe must live below this geometric ceiling. It defines the ultimate limits of artificial intelligence and simulation.
Speaking of the universe, what about cosmology? When we look up at the night sky, we see the universe expanding, and we know that expansion is accelerating. We call the invisible cause of this acceleration dark energy. But let's be honest, dark energy is just a placeholder name. It's a label for our own ignorance. We don't know what it is.
But under the geometry first paradigm, we might finally have a mechanism to understand it. If, as we discussed with ER equals EPR spacetime geometry, literally emerges from the entanglement of quantum bits, then the accelerated expansion of the universe might not require a mysterious new dark force at all. The expansion might simply be a natural thermodynamic change in the entanglement structure of the vacuum over cosmic time.
As the universe processes information, the entanglement network shifts and the geometry expands. It gives us a geometric information-based mechanism to finally explain dark energy.
And then there is the philosophical elephant in the room, the simulation hypothesis. This is the popular idea championed in pop culture and by people in Silicon Valley that our reality might literally be a giant computer simulation run by a more advanced civilization.
The Bekenstein Bound elevates the simulation hypothesis from late-night dorm room philosophy into actual rigorous physics. The bound gives us physical tools to argue computational metaphysics.
How so?
Any computer running a simulation of our universe must track the state of the universe. It needs RAM. It needs memory. And we established earlier that the maximum information capacity of the observable universe is strictly bounded by 10 to the 123rd bits.
Right.
This means any hyper-advanced computer simulating our reality does not need infinite memory. It only needs to process a finite number of bits. It mathematically limits the required hardware specifications of the universe simulator.
But it also goes the other way, right?
Mm-hmm.
It proves that physics has a built-in resolution limit. If you, inside the simulation, try to build an experiment that forces a region of space to hold more detail than the Bekenstein bound allows, the simulation doesn't just crash and give you a blue screen of death.
No, the universe's self-defense mechanism kicks in. Physically, it forms a black hole hiding the excess information behind an event horizon. Black holes might literally be the out-of-memory errors of reality.
That is wild. But ultimately, the highest stakes here are unified foundations. The 20th century gave us two great, incredible, but entirely incompatible revolutions. Quantum mechanics to govern the very small, and general relativity to govern the very large. The holy grail of physics for the last 100 years has been to unite them.
And the goal of this entire geometry-first program holography in the Bekenstein Bound is to finally forge that unification, to prove that gravity and quantum mechanics are just two sides of the same information-theoretic coin.
Which brings us to the Feynman verdict. If we step back and look at this entire deep dive through the pragmatic, no-nonsense lens of Richard Feynman, what is the core takeaway of everything we've discussed today?
Feynman would strip away the jargon and say this: space has a texture. It is not an empty passive void. That texture is made of discrete physical information. There is exactly one bit of information per Planck area on the surface of any space. That is an inescapable, mathematically proven physical fact.
The mission of modern physics, and the goal of every researcher tackling those six frontiers, is to take that single fact and mathematically derive absolutely everything else from it. Gravity, matter, time, causality, and perhaps even human consciousness. All of it must ultimately emerge from how those 2D geometric surfaces encode, process, and exchange information.
As we wrap up this deep dive, I want to remind you of the sheer scale of what we are talking about. If this research program succeeds, if the physicists listening to this tackle those six open directions and win, we will have done it. We will have the complete fundamental rulebook for reality. Everything else in human knowledge, chemistry, biology, engineering, neuroscience, sociology will ultimately just be highly complex macroscopic footnotes to the foundational rules of geometry and information.
And I want to leave you with one final provocative thought to mull over, something that wasn't explicitly stated in the source text, but is the undeniable logical elephant in the room if you follow the map to its conclusion.
Lay it on us.
We discussed that reality fundamentally behaves as a holographic surface, pixelated with exactly 10 to the 123rd bits of information. We discussed that the 3D bulk of our universe operates mathematically identically to a quantum error-corrected code constantly redundantly backing up data.
Yeah, the universe is a tensor network preserving information.
So if the geometry of space is literally a computational code designed specifically to preserve quantum information against random noise and corruption, then what or who is processing the code? Where is the macroscopic thermodynamic environment that this universe is trying to protect itself from? What kind of cosmic multidimensional errors is the fabric of our universe constantly silently trying to correct?
Wow. What is the universe protecting us from? That is absolutely going to keep me up tonight. And with that, we want to thank you for joining us on this incredibly dense, fascinating deep dive into the Bekenstein Bound geometry first and the very pixelated fabric of existence. We hope this roadmap has given you a glimpse into the bleeding edge of physics. Keep questioning the space around you because, as we've learned today, it isn't empty, it's holding all the secrets.